Hi everyone, welcome to Building with Naz. My name is Naz, and in today's live coding session, this video, I'm going to do a deep dive of testing. I had done another video recently where it was mostly around discussing unit testing versus integration testing versus end-to-end testing, and then kind of like scratching the surface with unit testing. But today we're going to actually do it for a real crate in preparation for it to be published to crates.io. So this is more of a representation of what actually would be done for real testing. The crate that we'll be writing a bunch of tests for is called this Rebel Terminal Async, and I've covered this in the last couple of videos where the whole idea with this crate is that I needed an async readline so that when I'm building command line interface or CLI applications, I wanted a way for asynchronous tasks, because I use Tokyo a lot, to be able to generate output to standard out, and I didn't want that to clobber the prompt that gets displayed when readline is used. And also the line editor, if you want to think of it, the line buffer or the line editor, I didn't want that to be clobbered by standard out. So that ended up going on this journey where I forked Rusty line async, I think, and pretty much rewrote most of it. And then added a whole bunch of other stuff to it as well. And then that's this new crate, Rebel Terminal Async. And so one of the things I did in preparation for this testing video is that I ended up actually, these are all the issues for this particular repo. So it's on Rebel Terminal Async. I'm going to move this into the Rebel Open Core repo that I have. I'm a maintainer of the this thing, Rebel Open Core. It's a text user interface library, and it has it has a whole bunch of CLI stuff in it as well, not just full TUI. And it will also host this repo whenever it's ready. So yeah, so one of the things I did to get the repo, this particular code base, ready for testing is that I tried to reduce the amount of code that I tried to simplify the design quite a bit, because I had forked it from another repo, and certain design decisions were made in that code base, and I wanted to simplify things quite radically. Let me give you a concrete example of this. Here we go. So this, and by the way, for this particular video, we'll be working on this issue. Yeah, this one, unit tests. And then there's a PR associated with it as well. So I'll link both of these to the video whenever it's uploaded to YouTube. So one philosophy with testing is that what are you testing? And so, like, if you can minimize the code almost that you have to test, then you have to write fewer tests. So this is typically not an easy ask, because a lot of times you can have a code base that you really don't have any control over, and you pretty much inherit it as is, and then you have to work around a lot of the complexity that that particular code base might have. Maybe the mental models are not intuitive, and it results in all kinds of other downstream impacts, which are not so ergonomic. And so in those scenarios, you might have to come up with some really sophisticated text fixtures and testing strategies to actually get at whether the code under test is actually functioning as expected or not. In my case, since I could just rewrite the entire code base because it's not that big and it's new, relatively new, I just decided that I would take essentially this one file. There's really three pieces in this crate or this repo that are of significance. Three files. So I took one of the files and I removed almost all the code in it, and that was this effort. And you can actually see what the it's in here. You can see what the PR looks like for this. And one of the main files that got impacted was, let's see, it was, where is it? Actually, a lot of things got impacted, as you can see, because introducing the file size to like roughly 1/3. Clearly, there were a lot of other changes that need to be made. But this one here, shared writer, this is the one. As you can see, like if you look at these little graph things, you can see like how much got added and how much got removed. So I should have just gone by this. So if you can see in shared writer, so much of it got removed and a little bit got added. So let me walk you through what this thing does so that we can figure out how to test it. So if you're curious, this is the code that got removed. All of this. Implement async write for this struct. And all that was left is a much smaller implementation of write for shared writer. So, okay, so there's async write and write, and async write got dropped basically to simplify things. So so let me just walk you through the code because this is the thing we're going to be writing a test for in just a few moments. So the main crate is here. So if you look at the librs documentation, there's just one entry point. That's not true. There's actually, well, okay, there's actually just one entry point, and that's this. And by the way, this is like how you can run the examples. I added some videos to show like what this thing looks like in in practice when you actually run it. Yeah, and there's videos for how this was constructed from the get-go. So check it out. Actually, let me clear this. So yeah, this is, you can just see it running here. This is sort of redundant, but this is what the videos are just showing. But yeah, so you can do up, down. It has history. You can start asynchronous tasks that and stop them. This is just an example, but it kind of illustrates that you have a command line interface, a REPL, which is quite sophisticated, and it has integration with Tokyo tracing. You can do all kinds of stuff. It's actually quite. This has turned out to be a really nice nice little crate that I intend to use for I would say applications that don't need a full TUI, but they do need more than just a sort of a one shot, one run kind of experience. So it's like somewhere in between. You have full TUI over here. You have like a simple command here, like rm-rf. You have something in the middle here where you need a REPL. It's going to do a bunch of async things. So imagine if you're going to build like Postman or something. You could technically do, yeah, you could actually build this. You could make a very simple kind of Postman in the TUI using this crate. Obviously, if you use TUI, then you can do something that looks more like the actual Postman. But if you wanted something quick that needs some interaction, that where you have concurrent tasks that need to generate output that need to be displayed, and you have an interactive prompt where the user needs to type something. Oh yeah, actually one of the coolest things about this demo is, so when you're, this is an interactive prompt, so you can actually go left, right, you can, it does history with up, down. So, and this is, by the way, this is all happening while other asynchronous tasks are concurrently writing to standard out. So this is pretty cool. So you can do this and see, you can go left, right. So it's stateful. And you can hit Control C, Control D, or you can just, in this case, type exit, and they just exit. Okay. So in order for, oh, and actually, this is the spinner. We're not really gonna do much with the spinner today because this is more for we're gonna write a test for readline because this is the main thing. The asynchronous readline capability comes from this. So let's see. It's kind of strange. Sometimes the output is buggy like this. That might be something to look into later. I'm not really sure if it's consistently a problem or I can see it sometimes. Anyway, okay, so let's look at readline. Oh, by the way, a real project in which this is used looks like this. So that was just a demo. This is a real world example of an interactive suit, like as interactive, like a REPL, read, execute, print loop. application where it's connecting to a TCP server, it's dumping a bunch of stuff from Tokyo. It showed a little spinner while it was connecting to the server. You can type commands like these are not implemented, and then when you hit exit, it just exits. So that's a real world use case for where this crate would be used. So let's see. What we can do here is let's go look at how this actually functions. So what I was getting at with this documentation, actually I'm going to put this here so we can see them side by side. So the first thing that you have to do to use this crate is you have to make a terminal async, and the terminal async is then what you primarily use as somebody who is using this API. So that capability or that functionality is in the public API module. So this is a very, you want to think of it this way, it's a very small surface area, the smallest surface area that somebody who's using this crate that they would need to know about in order to get some value from it, in order for it to deliver on what its promise is or promises are. Then we have this thing, spinner. That's another entry point where somebody wants a spinner. So in order to make a spinner, they need a terminal async. And that's roughly the two things that the public API is concerned with. Today in the test, because we're doing unit testing, we're going to be primarily concerned with not any of this. We're going to be concerned with how this terminal async itself is implemented. And we're going to go under the hood for terminal async. So when you make terminal async, when you say try new, what it does is it creates a new readline struct. And this readline struct is the thing that we're going to be unit testing. So the main function, I'll just cut to the chase. The main function is the readline function in the readline struct. So you create a readline struct. Let's see, where is it? Terminal async public API. Yeah. So you create a readline struct, and then just essentially wrap that in a just return it essentially, but wrap the readline itself in an arc mutex, because we're using Tokyo. There's a lot of threads. We're going to spawn a lot of tasks, and so we need something that's send and sync. So arc mutex is good for that. So let's come back to readline. So if I actually show you an example of this, let's see. Let me show you this demo. This one. I'll show you the code for this. So this is like, where does this happen? This is in the terminal async examples. So go to the main function. There we go. So the main function returns a MEAT result, and the first thing it does is makes itself a terminal async. And notice it doesn't really do anything with the readline afterwards. Like, except here, we're doing something with the history so that when you hit up down, it actually has stuff in it in the history already. So we're pre-populating the history, and that's where this readline shows up. But other than this block, we pretty much don't really interact directly with this readline struct. All this terminal async struct does is it exposes a function called getReadline event. That's what the public API is exposing. Under the hood, getReadline event literally turns around and calls readline, the readline method on the readline struct. And this is where we are right now. So if you look at the control flow, let's look at the mental model first, because we need to kind of, unit testing is kind of like in the weeds, but I think it's important to understand the context of where this thing is in order to get an accurate idea of like, okay, what to test, why are we testing it, what behavior are we expecting. So at the very high level, you have a process. It's your command line interface application, right? And then that command line interface application is running some code. That code is asynchronous. So the Tokyo executor is managing all the threads and everything, and it's exposing green threads so that you can spawn tasks, which is great. So here is an infinite loop in the main function that is this program. And it's not blocking. It doesn't even block on readline. So what it does is that it checks to see, remember there's start task 1, start task 2. So these are just made up tasks. You can literally start them, and all they do is they just tick. They're just intervals, Tokyo intervals. So what this infinite loop does is that it erases these futures. You're like, what? So it erases these futures. So it's called select, but it could have also been called race. So it's taking this future, that future, that future, running them all, and then whichever one finishes first, it will go with that one, and then drop the rest. So what this means is that if you don't do anything and you start at task 1, see that it just keeps generating output. It's because the delay is pretty short, and in this infinite loop, the interval keeps basically completing or expiring, whatever how you want to say it, and after that particular delay, this code path executes. So this wins the race if you don't type anything. Then when you do start task 2, all of a sudden there's a slower task, and this one is winning the race more than that one, because this is roughly 4 times slower. And then finally, when you type something, is when this branch or this branch of this code that you're looking at actually executes. By the way, none of this looks like this when it's expanded. So if you do cargo expand, you're going to see a very different code actually generated for this, because this is a proc macro, and async stuff gets expanded into essentially a finite state machine, where it's a continuation. I don't know if you're familiar with coroutines, but essentially when you call a function and it yields, when you call that function again, it will resume from the last yield point. And that is how this magic is implemented under the hood, which is why for asynchronous code, there's this thing called pinning, where you have to pin, essentially when you enter the first state and certain information or data has been allocated to memory, you have to pin it so Rust won't move it. So that in subsequent executions of that function, it's expecting to find everything exactly where it left off in the previous execution. So you'll see a lot of this pin mute, pin project, pin projection. These are all things that are related to asynchronous code, but most of the time people don't see any of that. I actually removed a whole lot of that in the shared writer to make it easier to run and test. So I hit Control D, and what it did was, as soon as I pressed Control D, it won the race, because it just so happens it was waiting for this one, or this one, and when Control D showed up, it got itself an event, and it was like, okay, I want to process this readline event, and it got something called control flow break, and so it just breaks out of the loop. That's basically what it does. And if we look at process readline event, actually, so here we go. So get readline event actually calls the readline function. This is the thing we'll be testing. And process readline event actually does something with the value that's returned from this function. So this one is part of the example, so we don't really care so much about this. We care more about what is happening here. So in get readline event, we go to the readline function, and this is where basically all the magic happens. So let's look at this. So this is the thing I spent quite a bit of time simplifying, because the simpler this code is, the easier it is to test. And also, like, it's sort of like making sure that I, as the author of this thing, am aware of like how it's actually put together under the hood, like what the connections are between all these different files. And some of the stuff gets pretty complicated, and it's easy to lose track of what's going on. So when we create a readline, let's go look at the readline struct. This is the thing. This is the system under test for right now. So with this readline thing, when you look at, so that was the context, right? So now we're zooming in into the readline. So this is like one function, one struct, which you call one function on it, and it essentially sits around waiting for you to type something. When you type something, it will report the thing that you typed. And that's all using crossterm under the hood to make this happen. So when we look at readline, the two things that it exposes are actually it obviously gives a method called readline, but also it generates these things called shared writers. And I will show you readline. Let's see, new. So when you create one of these, what it does, it makes a readline. It does a whole bunch of stuff. It makes line state. Line state is a struct that holds the when you're typing things in the line buffer or the line editor, and you can hit Control left and right and jump your caret. So here, when you say this is a test, and you go or left right, and even while other things are generating output, you can do this. The reason you do this is because that information about where the caret is, what the user has typed, and this prompt, all of this is actually saved in memory in this thing called line state. And what this does is that every time anybody writes this, the shared writer, which is the thing that is the concurrent standard out that it exposes right here, what happens is it actually deletes itself. It clears out the whole prompt. It displays the output to the standard out, and then it repaints the prompt. But it repaints the prompt to look like what it looked like exactly like what it was when you left off. So visually, it just looks like, oh look, something got added above the prompt. But actually, what's happening is that the prompt gets cleaned out. The thing, like for example, 58 just got printed, then the prompt got basically printed, and it just keeps going. And it gives a visual illusion that, oh, that's cool. It's just, it kind of like looks like it's an interactive prompt, but actually that's what's happening under the cover. So now all of the also the terminal gets put into raw mode, by the way. And that's how when you hit left, right, up, down, every single keystroke is then reported to essentially, let's see, this one, this thing, the event stream. So there is an event stream also in the readline. So there's a lot going on in readline. This is not trivial. It seems simple, but a lot of stuff. And it actually could be made even more sophisticated because, as you'll see in the testing, there are some limitations even with this current implementation. It doesn't lend itself to testing as nicely as I would hope. But that's okay. That's why we have refactors and rewrites and so on. Also, it creates a channel. We're not going to be messing with this so much in the test we're about to write, but the reason to take all this time to go over the intricacies of what this thing is because how on earth can we test it if we don't know what it is? So that's why sometimes well-written tests and well-written code, you can learn a lot about what the code does by looking at the tests. The caveat to that is that it has to be well-written code and well-written tests. And so, and it takes a lot of effort not to necessarily write the test. But sometimes it takes a lot of effort to write the test, but also to consider the design of the system so that the system itself is testable. And that's where dependency injection is a really powerful pattern to bring into one of the tools in the toolkit that you can use to make this happen. Okay. The reason dependency injection is so powerful is because it allows us to mock systems or even use test fixtures instead of the real system. So for example, we'll see some of these limitations here where the code has a lot of sort of expectations that are satisfied without dependency injection. So it's using a lot of things that we just cannot replace by providing a text fixture, because under the covers it's going to go use standard out, the real standard out, or it's going to use some other resource in the operating system, which essentially is in a way hard coded into the behavior of this program. It's not malleable. We can't like override it or change it in any way. So, and that's okay. Like it's a journey. Like not everything is going to be fully tested like to the nth degree, because it's a lot of effort. So you have to find this trade-off where you're like, okay, what am I testing? What can I test that will give you the maximum value? And so without having to like rewrite your whole code base so that it's really easy to test, which a lot of times with test-driven development, the thinking is that you should start with that idea of like, okay, write your tests first and then write your code to satisfy the tests. But rarely in practice does anything fit a mold. It's usually a blend of things, and it's a journey which twists and turns and winds its way. People think like progress is linear. It's really not. It's kind of quantum. A bunch of stuff will happen here that will unlock something over there in space and time, and then that might lead to something else and so on. And it's not linear. So linear thinking is not really the right mental model to have when approaching code bases testing, just to all of the stuff in general. So with that philosophy aside, let's look at what we'll be testing. So let's focus in on readline. So right away, there's a couple of candidates I can see for testing. So these are all very important. I think we should test line state, whatever that is. So then we have to go do a deep dive on what that is. I kind of already to give you a hint of what that was. It's a thing where you're typing and you can go left, right. It's the prompt with the line buffer. So this definitely we need to write some tests. Let me see if we have, yes, we have a little comment here, add tests. Read line for sure. Let's see. Oh yeah, this thing, I think there's a history somewhere I saw. Yeah, there it is. So the history, we need to add tests for that. Okay, cool. So we have that accounted for. I'm not saying we're going to get to all of it in this video, but we're going to definitely get started. So what this thing does is that, interesting, it just renders the line state and then flushes the terminal. Okay, got it. It says we don't know exactly what all this is right now, but we will know some of it anyway very soon. Okay, so if we look at, so that's new, right? So we're like, okay, that's interesting. There's a read line and a shared writer. So the shared writer, that's the thing we need to test. Yes, that is correct. And by the way, this is the thing that I simplified because it was way bigger, and it was using thing buff, and it was using I think pin project and all kinds of things that really at the end weren't even necessary, because we could just get away with what we wanted with a simple Tokyo MPSC channel. So that is one of those philosophical things where it's like, okay, I could write a whole bunch of tests, or I could just like simplify the system, which is a big ask, so that there's less code to test. There's less code to test. Naively, perhaps less test needs to be written, but that's actually not that bad of an idea. The fewer lines of code you have, like if you want to think about it that way, there's less to test because there's less code. So yeah, so essentially the code that was here before, the thing buff and the pin projecting and all that, it was completely unnecessary because there was essentially, we can just use stuff that comes out of the standard library, and we can use stuff that comes out of Tokyo. Just there's no need. The other problem with having all of these extra dependencies, this is a bit of a tangent, especially given the security vulnerabilities that were exposed, I think, with the compression library thing last week is that if you add a lot of things to your cargo toml, like that's another thing you gotta like maintain, meaning that whoever is the author of that crate or authors, are they funded? Can they do this? Do they have sustainable means to support the crate? And sadly, a lot of open source maintainers, the ecosystem that we exist in today doesn't really. There are no funds that, by and large, that can be allocated to open source maintainers so that they can do this and earn a living. Typically, people have to get their income from different sources unless they're financially independent. So that's a whole other. So the more things you add to your cargo toml, it's like, is that crate going to be unmaintained in the future? Who knows? And if it's, I'm not even saying is it going to be, compromised, which could happen if it's unmaintained and people don't have resources. Who knows? There's a whole lot of issues that are exposed with a broader problem of there's no financial incentive for maintainers to maintain these crates, and so the industry at large uses the value generated from these crates having been created and published, but then they don't necessarily give back. I mean, obviously there's exceptions like Tokyo, but unless unfortunately there's a lot of smaller crates that are not the size of Tokyo that are also super important because they get used everywhere or in some other larger system. And so it's kind of like you find the weakest link and that becomes a vector for exploitation or an attack. So, all right, that aside, okay. So this was, and by the way, this PR you can see. Too many tabs. There it is. In this PR, you can actually see like how I removed pin project and thing buff, and essentially replaced it with this code. So, okay, let's go back to readline. So let's look at readline function itself. So the readline function. So here we are. This is the readline function. So once the readline struct has been created, somebody at some point has to call this function. This is asynchronous and non-blocking. So you'll usually see this itself in a loop in a select. So it's kind of like this is incepting where we have like the example looks kind of like this. I don't know if you guys are Rick and Morty fans, but I was incepting from Rick and Morty. Here we go. Shared writer. Nope, that's not it. We are looking for terminal async example. Yeah. So see this loop select. I mean, we can make it look exactly like that by saying this. So that looks eerily like this. Pretty cool, right? So yeah. So this readline itself, when you zoom into it, looks very much like the event loop of that example we were just looking at. Where is that example? This one. Yeah. So there's a loop, there's a select macro, and then it's erasing these futures. And we have a similar situation here where we have a loop and we're erasing these futures. Look at that. So the path, the branch in this select statement, the one that we're going to be zooming in for the purposes of this is this code path right here. So I was looking at this yesterday because I was thinking about testing, and I was like, this is the way it looked before. I actually did some refactoring before I started this video. I cheated. Where I was like, okay, the way it is right now, it would be pretty hard to. This is the issue that's open for what we're doing in this video. And here's the code that I changed in preparation for the video. And let me collapse all this so you can see. I wonder if there's a way to collapse them all. Probably is. That would be handy. Can I collapse them all? No? Is that not a thing? Control K maybe? Collapse? No? Okay. Clicking it is. Let's see. So the changes that I made are to readline RS. This one. No, that's not the changes that I made. Thought I made changes. Wait, what? Am I in the right? Let me see. Or had I made these changes already in a different branch? No, that is here. I don't know what I don't know what I did with that view. Okay, that's just weird. So it is readline RS, and I don't know what. Okay, I have no idea. So okay, let me just close these because they were noisy. Oh yeah. Okay, where are we? No, 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 and yes. Okay, there we go. That makes more sense. So the way the code was written prior to this change is that all the code was like inline, and this is a procedural macro, and it expands. You can do cargo expand, and it's pretty cool actually. If you actually want to see what this thing looks like, you can go play with cargo expand. It's pretty awesome. So essentially, or you can I think depending on the IDE, you can also say, this usually says not available. I don't know what I'm doing wrong, but like in I've seen this work in Rust Rover. Yeah, whatever. There's supposed to be a way to expand the macros. Oh, oh, I see. So you have to be exactly on the thing that's a macro. So as you can see, this expansion, this expanded code, looks literally nothing like what is written on the left-hand side, right? So check this out. So remember I was telling you they get turned into a state machine, and there's pinning and all kinds of stuff. So there's that pinning, all kinds of things that the macro is doing on our behalf, so we don't have to see all of that. But anyway, so so right click on this on the macro and then say expand the macro, and it works every time. Okay, that makes sense. So here I was like, okay, how can you test this readline function? And I was like, I tried. So there's a couple of approaches we can take with this, but regardless, what I thought was like, instead of having the logic all inline laid out inside of the macro, I simply just refactored all of them into functions, created a module called readline internal, and I moved the code that was inline inside of that macro into a function. Right away, like, this is the thing we're going to test, because it's deep enough inside, it's disconnected enough, disjointed enough from its external context so that we can focus in on this system and test it. We can give it its inputs and check its outputs. So this is a bit of a trick where this function readline is very difficult to test, because it brings in all kinds of things along with it. Because when you look at new, you'll see how many things are in the struct. Quite a few. Like there's a line state and raw term and all this stuff, right? Look at this, standard out, boom, right there. This is that's using the standard library standard out. So what we would want to do if we created a text fixture for readline is essentially create a standard out that behaves like standard out, but then now we have changed the type. So we can't have it as standard out per se. It would have to be something that behaves like standard out. So it could be like a write or something. But then we have to change a whole host of other things to accommodate that. So it's not so simple to create a text fixture because um, it's kind of like this is where dependency injection comes in. So in dependency injection, instead of raw term being standard out, it would be something that's like a write. And then when we created the this thing, we would have to maybe even provide a wrapper or an implementation of that trait, let's say, and then for the specific resource that we actually want this readline instance to use. So, and then we would probably pass that in through the constructor. So this would also have another argument saying, the implementation of raw terms. So it'd be like raw term impl would be like something like that. So, but now this became more complicated, and so it's a trade-off, right? Like you can make it super testable, but then the ergonomics might start to go. But then you can provide a factory, you can provide a builder, and then you have a little bit more complexity on how to create a read line. So it's trade-offs. There's always trade-offs. So coming back to that function we were looking at, readline is the main sort of the main function that applications will use to actually derive value from this crate. And that right away, what it does is that it looks at this event stream, and the event stream is something that's provided by crossterm. And essentially relays when you type something. Remember the terminal got put into raw mode, so when you type A, B, up, down, every single keystroke, and mouse actually, events are then added to this event stream. So when this code goes event stream.next, it gets whatever keystroke you might have typed. So if you typed 2 or 3 keystrokes, they're all queued in the stream. So this is an async stream. So one approach is that, well, should we just make our own like event stream? We could do that. That's one way to kind of test this readline function where we know ahead of time what keystrokes we want to inject, and then we can test to see that does readline do what we expect it to do. So that's one approach. And the other approach is, well, we have a function called process event, which actually takes this crossterm event. Once it's been retrieved from the event stream, we can trust that event stream works. So we don't have to test this. We do have to test this loop though. This race select macro, like this branch versus that branch versus, these are 3 different features. So we can trust that select works. So then what we really have to test is, okay, does this work? Does that work? And does that work? Because if each one of these individually works, then this should work. And this should work. So that's how I broke it down. Because to create a text fixture is a ton of work, as I was expressing earlier. We have to like basically change readline again so that it uses a lot more dependency injections. We probably have to create a readline builder. And we can do that. It's not a bad thing. It's just that for this exercise, I think that there's a lot of value in testing this, because this is kind of like one of the main things that happens. It's like when you type something, like what happens? This is the thing when you type something. Because readline, it's supposed to take user input. So the single most important thing in this particular crate is the thing that takes input. The other one is it gives you concurrent writes. So we got to test that. That's a shared writer thing. And the third thing is there's a spinner, which is actually built up on top of other things. So we'll see how to test that later. Okay. So in that main the loop, which has the select macro, which races these futures, we can assume this works, this works, this works, but this is something we need to test. So the reason I turned this into a function and added all the strange control flow things, which I'll go into in just a second, is for this reason, so that this looks a bit awkward. Originally it was inlined, where I think the code was much more readable. It just like do the thing, but then I was like, okay, let's just remove all the logic and move it into a separate function, which required the creation of this strange thing called control flow enum. Then I have a match statement on that, and it's so that I can test the process event function in isolation. That's why I did this, so that I don't have to run readline to test this branch. I can just test this branch. So, and if you notice, I pulled a few things out of this the readline struct and passed them explicitly into this function, because this function, it's a function, it doesn't take self. And that was also intentional, because now I can test it without having a gigantic fixture. I can just provide my own line state, my own raw term, and then I can just run it. And the way I took this original code, which essentially in this code, there was a lot of ways for that code to return. Like it could continue, it could return with an OK, or it could return with an error. So there was a lot of things. So I couldn't just return one thing. So what I did was I created an enum called control flow. And control flow has like 3 variants. You can return an OK, you can return an error, or you can continue. If you return an OK, then this is a generic type called T, that this will that's the inner type. Then for return error, it's a different one. And for continue, there's nothing. So so essentially then I had to rewrite this original logic to return this enum rather than just actually calling the return function or the return keyword. So there was a bit of restructuring that had to be done, but it's a bit awkward because this is not the easiest thing to read. But that's roughly what's happening here, and this is the name of testing, basically. So so what it does is it takes a maybe, because this is there's an event which is wrapped in a result, which is wrapped in an option. When it gets wrapped in a result, you have to deal with the error type. And then all of this gets, basically we're just trying to get to this event. So it's like maybe is the option, result is the result, and cross-term event is this event. So I left out the error. So here the logic essentially it gets the inner value if there is some, and then if that's an OK, then meaning that we got an event. This is how I'm reading it. So then it calls this thing called line state to handle the event. So oh, okay, so we modify the something called line state. So we got a mental note. And also the raw term. So raw term and line state are 2 things that get used by this function. So that should be a little hint. It's like, oh, okay, interesting. So and then it returns this control flow. It's like, oh, okay. So it takes in a line state, it takes in a raw term, which is a mutable standard out, and it returns a control flow. So these are the ins and outs of this function. So if you treat it like a black box when we go to test it, this is very important information that we need. So, and all of this is like, okay, you got an event, and if you got the event, go give the event to this thing called line state. And line state will then unwrap that, actually not unwrap, it'll actually do something with the event and modify its state, hence line state. So if you hit a character, it'll be like, oh, you typed A. If you press left, it'll be like, oh, you move the character to the left, so then it's going to change the cursor to the left. Or what if you hit Control C? What if you hit Control D? And it's handling all of those scenarios. So this is also something we can test. Okay. So, but right now we're not testing line state. We're testing readline. So, and this is the main sort of logic in readline, which is process event. Okay. So armed with that knowledge, let's go look at what the test looks like. So usually what I'll do is I have test mod test. Yeah. Usually I'll do this, what is this thing called? I have an extension for this. Rust. Yeah, Rust flash snippets. It's kind of nice. Kind of like gives me these things so I don't have to keep typing them. So here we can put tests, and usually I'll do like a use super, something like that. Okay, so so then yeah, actually we'll need to, and then let's do a test real quick. Say we'll call this let's see, this test readline. Okay, so what we're going to do here is that we're going to test that. It's not really readline, it's more like test, what do we call it? Process event, I think. Yeah. So we're going to go test readline process event. And so if you look at process event, we have an event we can pass. We have some line state, and we have a raw term. Right? So what we can do is manufacture a stream of these. Because if you look at process event up there, it really gets all of these events from a stream. So that's called an async stream. And so we could do this. There's such a thing called async stream that's provided by Tokyo. And it essentially allows us to create our own little generator function that you can basically say, hey, just use a stream macro, and then they have some really good examples. So quite simply, you can use a stream macro to generate a stream of values that will be yielded asynchronously. You pin it, and then you just use it. So essentially, that's this thing. So we could mock this, but then we'd have to inject it somehow. And injecting it into readline is not trivial. As you can see, it doesn't take an event stream or async stream as an input, right? It doesn't, you don't see this like it's, where is it? Yeah, so it doesn't do like this impulse stream item equals whatever. Like that's not a thing. Like that's not, we're not passing this in as an argument. And by the way, it's non-trivial. If we passed it as an argument, it's not so easy because actually we could, but the types become really, really complicated if we do this. So essentially, like if we change readline so that you have to pass in, let's say, what stream you wanted to get information from, then it adds more complexity. We can do it, but it adds more complexity. So we'll explore this as an option actually once we test process event, because that needs to be tested anyway. So actually, what is this warning? Oh, right. So we're gonna let's test this process event. So the first thing we need here is we need a bunch of fake data. So we can say let input vec is, we're gonna say it is event key, yeah, something like that. So nope, not enter. We want, actually let's ask by, let's say a. Event a. Is that right? Let me see. And then we can clean this up a little bit. So we can do key event, key code, key modifiers. I think we can just say here, key modifiers none. And that is essentially A. Sweet, huh? So then we can do B, and we can do C. And then we can do enter, which is what it was suggesting this entire time is enter. So we can do A, B, and C, A, B, C, and then enter. So that becomes the sequence of characters that we're simulating somebody has typed A, B, C, enter. And that has somehow been relayed into this process event function. So if you look here, process event itself gets called by readline, which gets all of these from this event stream. So essentially we're like, okay, imagine this already happened. We are in here now. We've seen the A, the B, the C, and the enter, and we want to know what's going on with the control flow. So this is this sort of simulation, the setup. So now I want an iterator into this, and then let's now make a new readline. So we'll say readline, what is it? Is that right? Yeah, that's pretty good actually. Prompt, whatever. So we can, it doesn't really matter what the prompt is because we can split like this. And then we can say, this one is a shared writer. We're not really testing it right now. So I'm just going to be like, okay, don't really care. We just want the readline. Because remember, the process event is on a readline. So now what I want to do, because if you look at the process event, this one, yeah. Well, actually, this doesn't take readline, but this takes a line state, and the line state comes out of readline. So that's why we did this, because we're going to get the line state out of this to test. Because the line state is actually what, like when you say ABC enter, that information is actually going to end up in the line state. So we can just test to see if the line state has, you know, what we think it should have. Let's see. Okay, so we'll get the line state out of this to test. Okay, so we can put this here, and actually, is it line state? Oh, line underscore state. Okay. So okay, so now what we're going to do is simulate A. So we're going to do, let's get the event. So then we're going to say, so we're going to call, okay, this one, I'm just going to take its, this is control flow. That's going to come back. Actually, you can just say control flow, and then it takes a maybe. Okay, so it takes a, oh, it did that right. Wow, option result event, cool. So basically we take the event, clone it, because this is a reference, and then wrap it and all those things. And then it doesn't like this because why? Oh, okay, so it's saying that this needs to be mutable. So it's getting the line state from this readline, and the raw term is just standard out. So here we could do something more, I think. Okay, instead of standard out, why don't we just take the, we could put our own writer in here, even though unfortunately this is ampersand mute standard out, so it has to be something that implements standard out. So or not implement standard out, that is standard out. We can just say readline Roger. Okay. So again, with dependency injection, maybe we can inject something else in here to see what is actually being dumped to standard out. Because right now, as it stands, this test will pollute standard out, which we will see in a minute. So when I type A, this is correct. It should just continue. And when I type, what is the issue here? Control flow. Oh, right, because okay, this is a enum, And you can't do this. You have to say matches. And then you can't say assert EQ. You have to say assert. Okay. So there you go. So let's see what happens when we run this. Yay! It worked. Okay. So this is as far like that's just to simulate like typing A. So if we hit B, C, enter, you know, then you can imagine there's going to be like more simulate B and on and on and on. So this is good. Let's we can flesh that out. I'll probably do that in the PR after this video. I don't want to. It'll get kind of redundant. So let's try a different thing that I had mentioned earlier. Remember the process event was called by readline, and readline has this stream thing, and we were saying, well, what if we pass the stream in as like something like this, right? Info item equals whatever. I think it's event, yeah. Wow. Something along these lines. So it's like, okay, what would that look like? So how would we even sort of make a stream? So let's see if we can explore that in the remainder of this video. So let's see. For that, we would need to do something like. Okay, so we're gonna do something like test stream, and this is just like made up in the sense that we're not really gonna use it right now because it requires a whole lot of other structural changes to the code. But this is just like using this this code essentially. So let's just literally just copy and paste this here. Async stream futures core futures util. Okay, whatever. So let's bring these in. And that actually needs cargo toml. In cargo toml, I actually added these earlier because I knew we were going to be doing this async stream testing. And then let's see, we can do, okay, let's make a function that's like get input vec. So essentially like this, actually, you know what, we can just do this. Event is that. That's exactly right. And maybe we can make this part of our like text test fixture, because this we end up doing this get input event quite a bit. So we can say maybe we can just make this like that, and then we can do. Uh-oh, I did something wrong. Okay, then see. Okay, so we were making that a reusable function. Let's see. It should work. No? Get input vec. Oh. What the? Okay. Okay, so this one is, we can just make this here. We can just say, get rid of this and just say get input vec iter. What's the problem? Oh. Okay, cool. So now, okay, so here we were. So we need a way to generate the stream. So we can, inspired by that, we can say generate the stream, which implements stream item equals event. event and then get input back. Oh wow, totally works. Okay, so that's the stream generator function which we got based on this input back. So let's see if we can get a stream. The way we use it is that you make the thing, you pin the thing. This macro will pin like this shadows S. So what you're getting as in S subsequent to this line is actually the pinned S, not the S. I'll show you what I mean. So when you say pin mute stream, see, look, it moves this into there, and then it goes, I haven't used this stream because this stream is not that stream. So then we go, okay, so if we were gonna do a test, so we would do something like, okay, let's maintain a counter, and then let's make a loop. So let's see, how do we do this? No, that's not it. We can say while let event equals stream, which is our stream, this stream. Next, wait, okay, and then we can say assert something like that. Let's see if that works. It doesn't like it. It's a problem. Oh, right. Of course. So this is an async, and we need Tokyo test for that. All right. Okay. Let's see if this works. Oh wow. Nice. Okay. So this holds a promise, right? Because here we can say this is test generate event stream. So this potentially could be something that we use by and modify this one, because maybe readline should take a stream as an input, and then we could use like for testing purposes we could just provide a dummy stream, and then we could provide a like the real thing when we're not under test. And then also for standard out, because that's the other thing that's being manipulated here. The standard out could be mocked as well, so we're not providing a real standard out, so it won't like so when you run, like for example, let's see, you run these tests. See that? Greater than A. So basically what happened was when we simulated that prompt thing, when we simulate, it's kind of cool actually. So when we said that, okay, go ahead and type A into this read line, and remember we gave it a prompt, like, so for example, if we say $$ underscore, and now if we run this, check it out, $$ underscore. So that would be nice to test actually, because you know this is the prompt. It could be something like this. Doesn't matter. The point is that whatever that is, it's actually testable, and we're not testing it right now. What we're doing is that we're typing A, telling readline we typed A, and what it did was it updated the line state, and it did type A and piped it into the terminal. And it just standard out, so we can see it here, and it clobbered the standard out for the test. That's why it polluted the standard out, so to speak. So we could fix this by, instead of providing a standard out, we could give a trait and say like, hey, give me something that implements that trait. So these are all exercises, and then that would open. Then we can test the output that's coming out. So instead of just testing the control flow and the line state, we could also like do an assertion. This is made up. Assert something like, let's say, made mock standard out, and we could say like something like whatever, something like that. So, but obviously we don't have that yet. So So yeah, with that, I think this is good for today's stream. That was a lot of background information and a lot of heavy duty stuff on async stream and testing and how do you mock like user input events, and these are all non-trivial, and also exploring different strategies for how we can make this read line more testable by providing using dependency injection and a builder pattern, and using the builder pattern, providing a builder that allows you to pass in a standard out implementation, for example. It allows you to pass in like an event stream. Whether do you want to use cross term or do you want to use some made up event stream like this one we just made up right here. So those would be areas of improvement. But with that, I think this is a good stopping point for this video. I'm gonna do a lot more changes, put it into PR, and then whenever it's done, I'll mark the issue as fixed. So yeah, when the YouTube video comes out, there in the PR there'll be a whole lot more changes than what you see in the video. So with that, we conclude today's video. If you like this style of video, please give me a thumbs up and please subscribe. That helps me grow the channel because and also you can get notified when new videos are dropped. And also we have developerlife.com, which is this is the website for this is the YouTube channel for developerlife.com. Please subscribe because we have a newsletter, and whenever there's wow, that's a lot of prompts for subscribe, and so essentially you'll get notified when new tutorials drop or when new videos drop. And yeah, also we have a Discord. Link is in the description below if you have thoughts, comments, questions on this video. If you want to see other content, join in on discussions about command line interfaces, text user interfaces, that is the place. With that, thank you for watching and have a great day, and see you on the next one.